In this video, we will continue our look at nucleophilic substitution reactions, focusing on the SN1 mechanism. In our earlier videos, we saw that tertiary alkyl halides will not undergo SN2 substitution, but they will undergo substitution. So it must be happening through a different mechanism. Here we have a few examples of some nucleophilic substitution reactions, and rather than using a very strong nucleophile, we have a very weak nucleophile. Whereas hydroxide, HO- would be very strong, water is a much weaker nucleophile. However, it can still convert T-butyl bromide into T-butyl alcohol with HBr as a byproduct. Here we have a secondary alkyl halide, and we saw that secondary alkyl halides could undergo SN2 substitutions if they're treated with a kind of medium strength nucleophile. But here, once again, we have a very weak nucleophile, and this will react to give the alcohol and HBr as a byproduct. And in our third example, this is again a secondary alkyl halide. It will react with water to give some of this product and some of this product. Now, rather than having direct substitution at this position, we have our nucleophile became connected to this position. And so this is something that we had seen before, but the only explanation for how we get this product is if this reaction proceeds through a carbocation, and then if that's the case, this would be obtained by a carbocation rearrangement. So tertiary alkyl halides treated with a very mild nucleophile will undergo substitution reactions. For these reactions, the rate law has been shown to be equal to a rate constant K times the concentration of the alkyl halide. So the concentration of the nucleophile does not appear in the rate law. This reaction is called an SN1 substitution because that's the overall reaction that happens. Nucleophilic because it will involve a nucleophile, as we'll see in a moment. Unimolecular because there's only one molecule involved in the transition state of the rate determining step. If there's only one molecule involved in the transition state of the rate determining step, then there's only one molecule in the rate law. So what's going on in this reaction? We start out with our T-butyl bromide. Let's fill in those lone pairs. Now, it's possible for bromine to leave. It can take this pair of electrons that it used to share with the carbon, and it can steal them to itself, which will give a carbocation intermediate. That looks like this. Now, we have a carbocation. A tertiary carbocation is going to be high energy, but it's not extremely high energy, so a tertiary carbocation is reasonable. Now, what nucleophiles do we have present? Bromine is present, and if bromine adds to this electrophile, we're just going to go backwards. This is an equilibrium reaction, so that is going to happen to some extent. But we also have water present. So if water acts as a nucleophile, shares its electrons with the electrophilic carbon, then we are going to get a product that looks like this. This pair of electrons of the new bond came from the oxygen. It still has one lone pair, and now oxygen has a positive formal charge. But we still have more water around. Water's our solvent. So we've got lots of water molecules. So now this can act as a base, grab off one of these protons, allow these electrons to go back onto the oxygen, which will give us our alcohol product plus some H3O+. So our byproducts are Br minus and H3O plus, in other words, HBr and water. And our overall reaction takes us from an alkyl bromide to a carbocation to a protonated alcohol to an alcohol. For a nucleophile to add to a carbocation, that's going to be an easy reaction. Proton transfer to and from oxygen is an easy reaction, but formation of the carbocation, that is going to be a very difficult reaction. So if we think about our energy diagram, if this is the energy of our starting material, then maybe this is the energy of our carbocation. And so here's what the reaction pathway would look like up to the first intermediate. Now going from a high energy carbocation to a protonated alcohol, this is going to be much more stable. So maybe this is going to be down here in energy. We have to overcome an activation energy. We have to pass through a transition state to get to an intermediate. And this one will look like this. And then we'll get to our final product that looks something like this. So this is the activation energy of step 1. This is the activation energy of step 2. And this is the activation energy of step 3. I'm not being very precise thinking about the relative energy of these products relative to the starting material. We can look at delta G, delta H, other information like that. But in general, the formation of the carbocation, the transition state leading to the formation of the carbocation is going to be extremely high, and this activation energy is going to be the highest. And so the largest activation energy means the slowest step of the reaction. So step 1 is the rate determining step. If we think about the transition state for the rate determining step, we're going to have the carbon-bromine bond breaking, where the bromine is taking on a partial negative, carbon has a partial plus. But this is only one molecule in the transition state of the rate determining step. And so this proposed mechanism and the resulting energy diagram is consistent with the experimentally observed rate law. Let's take a look again at those examples from a couple slides ago, and let's keep practicing the mechanism. Now, here we have a tertiary alkyl halide, and we have a very weak nucleophile. First of all, this is not a very good nucleophile, so it's not strong enough to be able to attack this carbon and push away the leaving group. Furthermore, you can't do SN2 on a tertiary alkyl halide because it's way too crowded. So nothing happens until the leaving group leaves. So from our tertiary alkyl halide, we make a tertiary carbocation. When water adds here, we get this protonated alcohol intermediate, and then when another molecule of water grabs off one of these protons, pushing these electrons onto the oxygen, we get our final product. Sorry, all of these should be equilibrium arrows. So with a tertiary alkyl halide and a very weak nucleophile, this will proceed through a carbocation. And now that we have a carbocation, this is a really good electrophile. So even a weak nucleophile can react here, giving us this intermediate and finally this product. We've seen secondary alkyl halides undergo SN2 reactions, but that was with a moderately strong nucleophile. This nucleophile, again, it's still too weak, so it can't fight its way past the other groups to push away bromine, so nothing happens until the bromine leaves. When the bromine leaves, we generate a secondary carbocation. We still have our weak nucleophile, but now we've got a really, really needy electrophile. And so water can add to this carbon from either the back face or the front face. And that will give us this protonated alcohol, and then proton transfer will give us this alcohol. We started with a chirality center and we ended with a chirality center. So we'll talk about stereochemistry in just a moment. Now, in our third example, this is another secondary alkyl halide, but a very weak nucleophile, so nothing happens until the leaving group leaves. That is going to give us some of this secondary carbocation. From here, water can add to this carbon, which will give us, sorry, I usually try to do my color coding, but I'm all over the place. So here is our intermediate, and then another molecule of water will grab off this proton, put these electrons back onto the oxygen, giving us this product. But what else can happen? Now I'm going to redraw this carbocation. So this is our positively charged carbon. It is connected to a CH3, a carbon, CH3, CH3. We must have one hydrogen here and one hydrogen here. This is a secondary carbocation. But if this methyl group were to take its pair of electrons and share it over here, well, we would just have a new but still secondary carbocation. So that's not going to help. But if this hydrogen took its pair of electrons and instead of sharing them with this carbon, if it decided to share it with this carbon, then what will result? So we have our methyl connected to our carbon, methyl. This carbon is still connected to the one hydrogen and the CH3. It's now connected to the other hydrogen, and now this carbon has the positive formal charge. Remember, when we are using arrows, we are showing the movement of electrons, and then the positive charge results as we calculate the formal charge. We do not use arrows to show the movement of a positive charge. So we have gone through a hydride rearrangement, going from a secondary carbocation to a tertiary carbocation. Now from here, water can add at this position and it will give the tertiary protonated alcohol, and then proton transfer will lead to the formation of the other alcohol that we saw on slide 18. So carbocation rearrangements, it gives us evidence that carbocations are part of the reaction mechanism. So we just saw an example of a secondary alkyl halide that started with a chirality center, and because it's treated with water, this is a very, very weak nucleophile, so we know that this will proceed through an SN1 mechanism. When our nucleophile is the solvent, we can call this solvolysis. And we have a chirality center in the product as well. Given the mechanism for the SN1 reaction, what is the stereochemistry that we're going to have over here? Think about the details of the mechanism. When bromine leaves, we generate a carbocation. What is the structure of that carbocation? Keep in mind, the carbocation carbon is now sp2 hybridized. So we have our ethyl group, our methyl group, and our hydrogen, but this is now trigonal planar, and I have this drawn perpendicular to the plane of the screen. Now from here, water can add to this face, which will give us this intermediate, where here is our methyl and our hydrogen and our ethyl. And then after proton transfer, we get this product. So compared to our starting material, what we have is inversion of configuration. And more specifically, we are starting out with priority 1, 2, 3 with our lowest priority back. And then we trace 1, 2, 3 clockwise with our lowest priority back. So this is the R configuration. When we look at our product, this is priority 1, 2, 3, and our lowest priority is back. So now we are going 1, 2, 3 counterclockwise. So this has the S configuration. Keep in mind, absolute configuration refers to R versus S. Relative configuration refers to just the general appearance, the fact that similar groups have the opposite orientation in space. Now let's look back at this carbocation. We need to keep in mind that it's also possible for water to add to this face. If that happens, we will get this intermediate. Here is water with the positive charge. Here is our ethyl group, methyl in front, hydrogen in back. And then after proton transfer, we will end up with this product. We have priority 1, 2, 3, and 4. We are going clockwise, so this has the R configuration. And if we compare the structures, the ethyl's in the same orientation, the methyl's in the same orientation, the bromine is in the same orientation as the OH. So this one proceeds with retention of configuration. Given that this carbocation is planar, it should be equally likely for the nucleophile to add from the left face or from the right face. Therefore, we would expect a 50-50 mixture of the reaction proceeding with inversion or retention, which means a 50-50 mixture of S and R, which means an optically inactive racemic mixture. So we would expect a racemic mixture where our measured rotation would be 0. If we have the exact same amount of our R product as our S product, this is what we would get. However, what's observed in this case is a specific rotation of plus 9.6. 9.6. So pure S2-butanol has specific rotation of plus 13.5. R is minus 13.5. We got neither, right? We would need to verify by IR and NMR that we actually made this product, but then what is the optical activity telling us? We don't have pure R or pure S. We don't have a 50-50 mixture of R and S. What we have is a mixture of R and S, and we know because this is plus, we know that we must have an excess of the plus enantiomer. So what we actually got then was partial racemization. So we sort of made a racemic mixture, but with an excess of inversion, right? We have an excess of S. That's the one that proceeded with inversion. So what's going on? This picture that I drew was a little too simplified. And we need to think about the leaving group. Even though it has left, it has not necessarily traveled very far away. So once our leaving group leaves, it is going to be, let's say, over here, and it will be diffusing away. But depending on how long it takes between when the leaving group leaves and when the nucleophile adds, this leaving group might be kind of blocking this face. And so it's easier for the nucleophile to add from the opposite face, leading to inversion. It's a little bit harder for the nucleophile to add to the same face where the leaving group just left, and therefore we will have less of the retention. So the leaving group partially blocks one face of the carbocation. Now, how much racemization do we get versus how much of an excess of inversion? Well, it depends on the stability of the carbocation. If we have a secondary Rx, then we get a secondary carbocation, and that leaving group is still close by. And because the secondary carbocation is not very stable, the nucleophile is going to add very quickly. And so the leaving group will still be really close, and so we're likely to get lots of inversion. On the other hand, if we have a tertiary alkyl halide, when that leaving group leaves, we're going to get this, and then more time can pass and we get this, and then here's our X minus way over here, and now the nucleophile can add to either face. So the more stable the carbocation, the longer it can exist, and so that gives more time for the leaving group to leave, and therefore more space for the nucleophile to add. So what you tend to see is with tertiary carbocations, you get more racemization, closer to 50-50 inversion and retention. With less stable carbocations, you get partial racemization with a huge excess of inversion. Now keep in mind, I'm giving you this information as a way to explain what is experimentally observed, and I'm going to ask you to predict the stereochemical consequences of an SN2 reaction versus an SN1 reaction. But also keep in mind that this information also gives us support for the proposed mechanism, and it gives us information about relative stability of secondary versus tertiary carbocations. And so this information is useful in a theoretical way to be able to learn about different parts of the reaction mechanism, as well as being of practical value to be able to predict what product or products can be formed.